Let's start the seminar now. Today we have the pleasure of having Matt Johnson with us. Whoops, 1 second. Okay. We have the pleasure of having Matt Johnson with us. He's a research scientist at Google Brain, interested in software systems powering machine learning research. He's the tech lead for Jax. When moonlighting as a machine learning researcher, he works on making neural ODEs faster, automatically exploiting conjugacy in probabilistic programs, and composing graphical models with neural networks. Matt was a postdoc with Ryan Adams at Harvard Intelligent Probabilistic Systems Group and Bob Datta in the Datta Lab at Harvard Medical School. And before that, he was with us here at MIT EECS, where he worked with Alan Willsky at Leeds on Bayesian time series models and scalable inferences. I only met Matt today, but before that, I had seen a lot of his responses in the Jax helper documents, and I could see how dedicated he is to making Jax even more awesome and being just helping people that can introduce to Jax. My experience with Jax couldn't be better, and I hope you will also get some of it today. Matt,
all right.
I think we cannot see your screen. If you could share it now.
Yes. Here we go. Let me know if you can't see that. Otherwise, I'm going to assume you can.
Yeah, we can see. We can see it.
Great. Okay. Yeah. Thanks everyone for coming, and thanks for the introduction. I'm going to talk about Jax. Not any of that machine learning research stuff I used to do. I am presenting on behalf of the Jax team, which is like 12 or 13 people now. So keep in mind that like this is, any cool stuff you see is probably not my work. It's probably someone else's. Anyway, great. Let's jump right in. So I would like to just, some of you may have seen Jax before. If you haven't, hopefully this will like get you up to speed with a sort of whirlwind tour. If you have, maybe you've even seen some Jax talks before. I think there would be some new bits in here for you. So to motivate Jax, just from the beginning, we can ask this question of how would you implement a deep neural network from scratch in Python? So what does from scratch mean? So when I was a grad student, we used NumPy for everything. I guess we switched off of MATLAB, but NumPy was the new thing that everyone used. So you could say, how would you write a neural network if you just had NumPy available? And actually, you could do quite a good job. So here's a simple, fully connected neural network. We've got some NumPy calls for matrix multiplication and some element-wise nonlinearities. Obviously a toy example, but there's no problem sort of writing a simple neural network prediction function. And then you can also write a loss function just with NumPy, right? So here's a squared error kind of loss function. And with this, we've now specified how our neural network makes predictions and when we know it's doing a good job. So in some sense, we're sort of done. And this is just to say that even on this, even though this is a toy example, somehow NumPy gives us enough to express, how to, write a neural network on its own. What is missing from this picture? What would we demand to actually have a sort of end-to-end example? So some of the things missing are with NumPy is the ability to project onto accelerator hardware like GPUs and TPUs. So NumPy runs great on the CPU, and it's great for expressing these computations, but we want to run them on accelerators. Another thing missing is to be able to train the parameters of this neural network computation that we've written. We might want some automatic differentiation, and that is not built in to NumPy. So that's another missing piece. Furthermore, if we're going for really the most performance we can get, we might want to ask for something like optimized end-to-end whole program compilation with fusion and optimization of memory layout and maybe sort of smart rematerialization decisions. That also is not something we can get sort of just by writing this program in NumPy. Another thing we might ask for is, for example, if we're doing some differential privacy application, we might ask for vectorized batching, so we could write differentially private SGD. I'll say more on that later if that's unclear. And finally, we might even want to parallelize over a whole bunch of accelerators to really scale up our computations. So the point of this slide is to say that NumPy solves part of the expression problem of expressing the computations involved in neural networks. We just need these missing pieces on top. And so Jax is about giving you those missing pieces. This is Jax in one slide. Obviously, there's a lot to take in, but just to highlight, Jax gives you a sort of NumPy API. So we've changed the imports to import jax.numpy as JNP. And it gives you these things that we think of as function transformations. GRAD for reverse mode automatic differentiation, JIT for end-to-end optimized compilation and execution, and VMAP for vectorized batching, which again, you'll understand more of in a minute. And so the idea is that together with the sort of NumPy API and these function transformations on top, we can express a lot of the computations you might be interested in neural networks for training neural networks and doing all kinds of fancy things. And of course, to harness accelerator hardware, Jax behind the scenes uses this XLA compiler to project onto TPUs or GPUs, also CPUs if you want to use those. So that's Jax in a nutshell. To go over it in a bit more detail, I'm going to attempt a live demo. In fact, never before seen, I'm going to attempt 2 live demos at the same time. We'll see how that goes. So one of the things that we realize when we give Jax demos is people are always a little more like surprised than we expect that it works on GPU and on TPU. Let's just go ahead and like kernel, restart, clear output, boom. And so I have 2 versions of this demo here. One is connected to an 8 GPU machine on cloud, Google Cloud, fine cloud provider. And the other is connected to, we can run this correctly, a TPU, cloud TPU. So here we have this demo for 8 GPU devices that we have sitting here. That's great. I guess we could also do like, what is it? NVIDIA SMI. We can like look at all these nice V100 GPUs we have attached here. Cool. So I thought, usually we run the demo on one or the other, either on GPUs or on TPUs. I thought I'd run it on GPUs, but then also show you that the exact same code with no changes runs also on a TPU. So let me run this. Of course, there's twice as many chances for failure in this live demo. All right. So let's dive in. The basics of Jax, which, by the way, I would have killed for in grad school when I was at MIT, is to have a NumPy that worked on GPU or on I guess TPUs didn't exist when I was in grad school, but I would have loved for a NumPy that worked on GPU. So let's take a look at that. I'm just going to import jax.numpy as JNP. And Jax has a sort of like functional random number generator. Details are not important, but just if it looks slightly unfamiliar, we're just using Jax's random number generator. So here is generating. We're only using 1 GPU for this part of the demo. I'll let you know when we use more. This is going to generate a 5,000 by 5,000 flow32 array, and let's do NumPy stuff with it. We can like multiply with itself and print the results. You might even say like, maybe this is regular NumPy. How do I even know I'm using the GPU? Well, one thing you could do is you could look at these objects. These are sort of Jax device array objects. And the reason we print this out as a device array is when you're using Jax NumPy, the sort of memory, the values that you're operating on will live on your accelerator, like in your GPU memory, and they'll stay there. So when you dispatch Jax NumPy operations on them, you're just like operating on the GPU. We only pull values back to the CPU if they're needed for printing, like we just did here, or for plotting, like I think we do next. Whoops, here we go, plotting. Or if you have Python control flow, we only pull back the values that you sort of need on the fly. So, this is, Jax NumPy on the accelerator. You might also say another way that you can tell that we're using Jax NumPy, not the original NumPy, even though you can do all these fancy, NumPy indexing, all that stuff. That's all just there. Another way you can tell that we're using an accelerator is if we multiply this 5,000 by 5,000 matrix by itself. It can be done in like 19 milliseconds. And on a CPU, like a high-end Intel CPU with MKL and all that stuff, maybe it's like 200 or 300 milliseconds. So like this is clearly running on accelerator. But otherwise, it's you can maybe think of it as just faster NumPy. That's certainly what we aim for it to be like. Let's see if we can do that exact same sequence of things on the TPU with less talking. So we can generate 5,000 by 5,000 matrix. We can do dots. We can plot things and print things. Oh, I don't know if I restarted this kernel. Restarting clear output. I had done restart and run all. That's what I'd done before. I don't like when the input counter is like, not starting from 0. It seems like maybe I'm hiding something. So we got these TPU devices. We can do these Jax operations. Running on a TPU, this code is the same as you can see with your eyes. And this is not meant to be like, these are maybe different generation TPU and GPU, I forget. Again, also just doing matrix multiplies on these big matrices super fast. You'll notice on both the GPU demo and the TPU demo, when I did this little micro benchmark, this timing thing, I added this block until ready on the end. Usually you don't have to write this. The idea is that Jax will do computations. It'll dispatch computations to your accelerator asynchronously. So when you say jnp.xx, it doesn't wait for the result. It just dispatches it and moves on. And it'll only block block the Python thread waiting for the result if you ask for it, if you want to print it or plot it or save it to the disk or something like this. So for micro benchmarking, very important to add this little block until ready, because we want to time measure the time it takes to evaluate this dot operation, not just the async dispatch. Some people, like, one of the classic mistakes that makes me cringe is like, people will tweet and say like, oh my gosh, Jax is able to run my giant ResNet in like a nanosecond. It's so fast. But really, maybe they made the mistake of not writing block until ready to wait for the. So Jax is fast. It's not like faster than light sort of fast. So don't make that newbie mistake of writing block until ready. Cool. So that's hopefully cool that we're running the same exact code on a GPU machine and a TPU machine. So accelerator back NumPy, pretty cool. But maybe you've seen it before. What else does Jax have in it? It also has Autodiff, and in fact, I would say that Autodiff is something that sort of sets Jax apart. That was our original. That's how I got into the game of writing these kinds of systems. I'm just gonna show you an example, scratching the surface of how to use Autodiff. Maybe the most simple Autodiff transformation that you can use from Jax is grad, and it does reverse mode Autodiff like you might need for training a neural network. So here it is on a sort of toy example. This is a Python function. We got some Python control flow. If x is greater than 0, evaluate this cubic thing. Otherwise, evaluate this linear thing. And you can use grad. Grad is it's a higher order function. And Jax transformations, when we talk about sort of these transformations that are added on top of NumPy, the way to think about it is these things usually take in like a function, like a Python callable, and give you back a new function, like Python callable. So grad in particular takes a Python callable f and gives you back a new Python callable that we can apply to inputs here. If the Python callable f evaluates a mathematical function, then grad of f, the Python callable grad of f, evaluates its gradient. It's like mathematical gradient. That is the contract of grad. In this case, we just have scalars in and scalars out. And I'm just printing grad of f at x and negative x to show that we're exercising both sides of this this conditional in Python. One nice thing about this sort of functional Autodiff API, function-oriented Autodiff API, is that it's very easy to do higher order Autodiff. In this case, we can just call grad on its own output, and we can do higher order Autodiff. Just keep doing grad, and that's it. And so actually already just with sort of like accelerator back to NumPy and reverse mode Autodiff with grad, now we have enough to run like a simple neural network. In fact, that same neural network that we had on that intro slide. So here's a neural network prediction function, just fully connected MLP with matrix multiplies and a loss function. And then here's just some simple code to initialize totally random parameters and like random data. Nothing interesting. And we can say, once we've initialized these random parameters, what is our loss value, given our batch of inputs? And then we can run some steps of gradient descent. This is, I guess, full batch gradient descent. We ran 30 steps with some step size, and the loss went down. And that is deep learning. That's all we need for the singularity. So great. So we have like accelerator back NumPy, and grad is an easy way to use reverse mode Autodiff. As I said, Jax's Autodiff really, I think, sets it apart. And this example is really just scratching the surface. There's all kinds of other Autodiff goodies in Jax if you want them, like forward and reverse mode Autodiff. You can totally compose with one another. In particular, that means we can evaluate Jacobians and in particular Hessians sort of as efficiently as possible. It's got great support for complex numbers, like both holomorphic and non-holomorphic function differentiation. We even have some experimental features for doing exponentially faster, very high order Autodiff. And if you're sort of really pushing the extremes of performance, you can do advanced things like have precise control over what values are stored by reverse mode autodiff for the backward pass. Some of these things are documented in the Jax Autodiff cookbook. Let me just, again, for the sake of giving you 2 demos for the price of 1, let's run that same stuff on TPU. You actually can't really tell the difference between GPU and TPU. Maybe one interesting thing is that up to maybe small numerical differences, not only can you run Jax code on the CPU, GPU, or TPU, but things like random numbers are the same. So like if you generate a bunch of random integers on the GPU and then you switch to the TPU, the Jax random number generator will work identically across those things. So like you never have to worry about that kind of difference. One issue is that like unless you're careful about numerics, you can see some like floating point divergences. Probably if we print this loss function, they're probably slightly different for that reason. 2976, 2974. That's a bigger difference than I thought. Anyway, these things are like even random numbers you can make like precisely the same across backends, though maybe not floating point arithmetic. Great. So let's move on to another transformation. Even though with Jax NumPy and grad, you might be pretty happy about doing neural network research. There's more. So JIT is another function transformation API. This one is for end-to-end optimized compilation and acceleration using XLA. So as I said, XLA is this sort of super optimizing linear algebra compiler that sits behind Jax. And when we're calling Jax NumPy sort of like one operation at a time, we're just giving it one NumPy function at a time to optimize. And XLA, the people who put a lot of work into it, they want to optimize a bigger chunk of your code. They don't, they want their compiler to like see your whole neural network or your whole, optimization update step, and have XLA just like optimize the heck out of it. JIT is the way we stage out computations to XLA. And if you like, it's a way of building your own kernels. So you're not limited to the sort of GPU kernels that your library ships with. You can invent your own kernels just using JIT. So let's take a look at that. We can import JIT. We'll make another one of these big random matrices. Here's just a totally toy example that I chose because XLA can optimize it well. So this is just going to do some element-wise operations on a big matrix. It's actually only using a subset of the result. And we can apply F to our big random input, and we get some arbitrary big matrix of results. And that was operating on the accelerator, but it was sort of operating for every operation. It was dispatching an accelerator computation. What JIT does is it lets us stage out the entire thing to XLA. So actually, the Python callable you get back from JIT has the same input-output behavior, up to maybe floating point details, has the same input-output behavior as the original function. So if you memorize one of these numbers, like 1949895, 1949895, F and FJIT are producing the same output given the same input. What's different is how it's being computed. And so if we do a little timing microbenchmark, we'll see that this is on the GPU side. We've, if we're sort of executing this op by op, as we like to say, it might take 9 milliseconds. But by jitting it, it's gone all the way down to like 50 microseconds. Of course, this is like results are not typical. It depends on what your workload is for how fast, how much XLA can optimize it. This example is just showing off that XLA will do things like fusion of operations together, and it'll notice that you're only using a subset of results in this toy example. But basically, JIT makes your code run fast. Let's actually just let's run the TPU demo on the same thing. We'll see we're getting the same exact numbers in and out for those random values that we generated for the JITted and the non-JITted version. And if we time it, it's taking some amount of time. Great. So maybe here's a slightly less toy interesting example is let's take that loss function, the neural net loss function we had, and let's JIT that. And we can see that if we evaluate the JITted version, we're getting the same values out that we did before. But of course, we're going to evaluate it much faster, this JITted version. So maybe we're getting like a 2 or 3x speed up on this less toy example on our neural network. You can also compose these things together. Having a fast sort of like JITted prediction and loss function evaluation, that's great. But for training, we want to JIT the grad function. So let's just like JIT the grad function. And that is also going to be faster than it was before. Now we can just run another 30 steps of gradient descent. I'm not sure if it was noticeable, but like that was actually like much faster. And indeed, our loss has gone down again from 600 something to 329, something like this. So JIT makes your code fast. Why? Like maybe we can use JIT everywhere. Maybe we can take our like Django web server in Python and put jax.jit on it, and it'll be faster or something, right? So no, there's multiple reasons why that won't work. One is that XLA is specialized for numerical computation, in particular sort of big bulk array numerical computation. But another thing is that JIT itself has limitations in what we can sort of stage out of Python. Luckily, you'll always get a loud error if something goes wrong, but it does have some drawbacks. And so, for example, with JIT, when we JIT a function, instead of sort of like evaluating every Jax NumPy call eagerly, it means fundamentally we're delaying computation. So we're saying like, instead of running your code and letting you step through it, for example, in a Python debugger and look at all the values, we're going to delay the evaluation of this thing. We're going to stage that code out so that we enhance the XLA so that XLA can optimize the computation and then execute it. But by staging and delaying computation, that makes debugging harder. So when we don't use JIT, you can just have print statements and like PDB debugger and all that's awesome. When you use JIT, it means that your code could be harder to debug. Also, things like Python value-dependent control flow. So I mean that if x greater than 0 example, for example, that won't work with JIT because when we stage out this computation, basically we won't know when we're evaluating the Python if x is greater than 0 because we're staging out the value of x. Maybe if x were some intermediate in the middle of your computation, we're trying to stage out, we're trying to delay its computation, so we don't know its value. We can't tell Python which of these branches to take. And so if we try running this, we saw this work earlier. We saw it work with grad, so grad doesn't have these constraints. But if we JIT this function, suddenly we're getting an error. We always like to improve our error messages. This one's a little bit verbose, but it's actually telling you exactly what's going wrong. It's saying you were JITting a function f at this line of code, but the concrete value that you wanted, if x greater than 0, was not available because it depends on the value of the argument x. And that basically JITted functions, you can't have Python control flow that depends on the value of arguments. One last limitation, this is actually a limitation for all of Jax's transformations, is that the code you write has to be functionally pure. And that basically means that if you have any side effects, like your function appends to a global list or something like this, JIT, the JITted version won't faithfully capture that. It wants to see functions that are just math. And that's true sort of throughout Jax. I would say this is actually like, this is in a way a limitation, but actually our users have, honest to God, they always say that they love it because functional code actually brings it closer to math. And because we have an optimizing compiler behind the scenes, that means we don't have to worry about the kinds of mutation programs that you might have to write for performance otherwise. So for example, with NumPy performance, you might need to sort of like say, oh, I got to reason about this buffer and I got to make sure I'm doing in-place updates. With Jax and XLA and JIT, it'll figure out how to do in-place updates for all your buffers behind the scenes. So it's actually much more performant to write functional code. Cool. I don't know, I'll just do this like the TPU version of the demo. Lots going down. That's great. Same error if you run this non-functional code. TPU and TPU, same stuff. Great. So that's Jax NumPy, grad, and JIT. By the way, with JIT, what we usually recommend is you don't have to use JIT at all. You can just like use Jax NumPy. Another way to think about it is you can just have JIT in library code, and then you can just use Jax NumPy in grad, and then you're happy. But oftentimes, to get the best performance, you need to use JIT. That's sort of like Jax's big performance sledgehammer. And so a good way to develop is to write code not using JIT. And then when you want to get performance, when your code is sort of working, you can just apply JIT to the biggest subroutines that you can. Maybe that's your whole neural network. Maybe that's your whole optimizer update step. Maybe it's your whole training loop. You could apply JIT to these things, and you sort of JIT the biggest chunks of your program you can. And then outside of the JIT, you're back to this model of like Python eagerly executing sort of kernels on your accelerator. We actually put JIT on all the Jax NumPy functions. So like that's one way to think of like the way we write our NumPy functions is we JIT them under the hood. And you can sort of pull up the JIT into your user code if you want. Great. So Jax NumPy, grad, JIT, VMAP. VMAP is another transformation. We have like dozens of quotes where people say it is their favorite transformation, and yet it is the hardest to explain. And I never feel like I do it justice. So here goes. Here's an attempt. So VMAP is another transformation. As you might guess from the name, it actually just expresses a map. It's a map over an array axis. So here's a simple thing. You could map the like square function over an array. And sort of it gives you a new function, which also takes in arrays and outputs arrays. But it's sort of mapped the computation of this function over an array axis. So semantically, it's the same as when you VMAP a function and apply it to sort of stack of inputs. It's the same as semantically as having a loop over slices of your input, applying the function to each slice separately, and then stacking up the results. So if it is semantically identical to just writing a Python for loop, why do we have this thing, and why is it people's favorite transformation? So the difference is not in what it expresses. It's in how that computation is carried out. So the V in VMAP stands for vectorized map. And it basically takes this loop that we've expressed when we write a VMAP, and it plumbs this sort of batch dimension, if you like, through all of your operations. So it doesn't keep it sort of as a loop at the top level. It plumbs it through all of your primitive operations like we are used to doing manually in some libraries like NumPy, where you write code where it's like, well, I got to assume there's a batch dimension here for generality. VMAP will actually add those batch dimensions not only to your code, but to code you didn't write, to library code. You can sort of like, oh, they didn't have a batch dimension in this library. I'll VMAP it. That'll plumb a batch dimension through automatically. So to give you some example, here's a simple function that computes an L1 distance between two vectors. And it even asserts, it's like, I only want to see vectors. These should be rank 1, if you like. And then I will compute, basically because like, higher ranks, I didn't want to bother to think about adding a batch dimension to my code. So it's too hard to think about. Let's just write the vector case. So that's this L1 distance function. Let's make a just random input. Think of this as like a stack of 100, length 3 vectors. So this is 100 by 3. It's like 100 size 3 vectors. We can compute all of the pairwise distances between all these vectors. That's an array of size 100 to 100, where the ij entry is the distance between the L1 distance between vector i and vector j. We can compute that using VMAP by applying VMAP to our distance function, which only takes in vectors. We'll VMAP it twice. And I claim, it's a little bit of a head scratcher, but this will actually compute all the pairwise distances. Certainly the shape is correct. And if you look at the values carefully and compare it to a loop, indeed is right. But the interesting thing, as I said with VMAP, is how it's computed. So I'm actually going to import a little sort of pretty printer to peel, open up the hood, to lift the hood, and like show you how Jax is performing these computations under the hood. This is going to show us how is this pairwise distances function, which was a double VMAPed L1 distance, how is it actually going to compute things? And we can see there's no loop of size 100, or even like double loop of size 100 to loop over all these input vectors. Instead, we just have this vectorized computation where this is actually, if you stop and think about it, this is how you might write the pairwise L-wise distance in NumPy. We have to do some broadcasts, and then we do like a element-wise subtraction on the whole 100 by 100 by 3 batch matrix. Then we compute the absolute values, and we do a reduced sum at the end. So VMAP basically takes what we're used to writing in NumPy, plumbing batch dimensions through. It'll plumb batch dimensions through for you. It's quite convenient. It makes some shape errors impossible, which is interesting. But more importantly, even if you might say, I'm used to writing batch dimension code by now. I don't have to I don't need VMAP because I'll just plumb batch dimensions. That's fine. That's true for your own code, but you can use VMAP to add batch dimensions to code you didn't write. Maybe even code that no human wrote. And by that I mean, for example, if you have an Autodiff in the mix, Autodiff is sort of writing code for you, right? It's generating code that's not written in your Python text file, and you can use VMAP to add batch dimensions to code, functions produced by Autodiff. So, for example, to compute per example gradients using that same neural network loss function example we had before, we can do that by composing grad to get the gradient loss with VMAP. And the way I've written this VMAP is it's saying compute per example gradient, sort of like I want to map over the leading axis, the one at index 0, for my data inputs, and not map over my parameters at all. Why not JIT it? Great. And again, you can sort of poke at the numbers and make sure these are correct. But our batch size was 128. And so this is basically showing us that we're getting per example gradients. This is our gradient for our first parameter, which was this shape, but we have one gradient for each for the loss evaluated at each example. So, this is starting to show why we like to use the word compositional, or a function composition or composable transformations when we talk about Jax. You can express a lot of sophisticated computation by composing up multiple transformations. In this case, some per example gradients. People also do things like they'll write a simulator, and then if they want to, look at how that simulator works over many possible initial conditions or many possible like parameter values or something, you use VMAP and you get an efficient simulator that works for a whole batch of initial conditions. Great. So let's jump over to a lot of redundancy. TPU code, same thing. Great. Really, it's a little bit boring to switch. I'm realizing now between the GPU and the TPU version because they're just identical. Let's look at parallelizing over accelerators. So to this point, this demo has been using one GPU, but we have 8, and we're charging Google's charging itself a lot of money to run this like 8 GPU VM for this demo. So let's start using more of these GPUs. So the most sort of fundamental way, not the only way now, but like the most sort of simple way to use multiple accelerators is PMAP, yet another map. So it has the same semantics as VMAP. I think it takes a second the first time because it's like starting up nickel or whatever. Same semantics as VMAP, but as the name might imply, we are going to parallelize. P might stand for parallelize. And so in particular, we're going to parallelize over all 8 of our GPUs. So when we do this computation here now, instead of vectorizing over a batch, what we're doing is we're actually squaring each one of these integers on one of our 8 GPUs, which is kind of wasteful, not a good use of GPU resources, but it's a good example. Also, just FYI, when we use multiple accelerators, Jax has these sharded device arrays. We print this out when you look at the repr for some value. And the reason for indicating this is that actually we lazily keep shards of this array, in this case, just this simple length 8 vector. We keep shards on each GPU device's memory. And we only collect them back together and bring them to the host when we need them for something like printing. Great, so let's look at a slightly less trivial but still toy example. In this case, we can use PMAP to generate a 5,000 by 5,000 array on each of our 8 GPUs. So we have this MATS. Logically, it's just an 8 by 5,000 by 5,000, but actually, I claim under the hood, it has a 5,000 by 5,000 matrix on each of the 8 GPUs. So that was PMAPPing sort of a random generation. We can PMAP our dot function and then PMAP a function that takes the mean just to look at that result. And let's do that again because I bet it was slow because it was the first time, it was just in time compiling. Indeed, we do these matrix multiplies sort of in parallel. We're using all 8 GPUs. In fact, to prove that we're using all 8 GPUs, we can use another micro benchmark. And you remember it took like 19 or something milliseconds to multiply one 5,000 by 5,000 matrix by itself. Now we are multiplying 8 of them in about the same amount of time. So that is just to prove to you that we're doing stuff in parallel. And again, even using the fancy magic of running parallel over many devices, this has 8 TPU cores. The TPU device we're connected to, there's 8 TPU cores. And so we can program all of them super easily just by using PMAP this way. And again, it's sort of doing it in the time that it takes to do just one matrix multiply. So PMAP, actually VMAP as well. PMAP lets you do a bit more. Oftentimes when you parallelize, you don't want to do just a pure map. You might want to do things like some kind of collective operation, like an all reduced sum over some axis of your array. Or you might want to shuffle data around between your devices or something like this in the middle of your computation. And so PMAP and VMAP actually give you ways to express this, even though these aren't sort of pure map computations. You actually have access to collectives. So if you're familiar with like MPI collectives, very much the same idea. So this is just a sort of toy example to normalize a vector input that we're PMAPPing over. What PMAP and VMAP let you do is bind an axis name. So that's sort of naming the axis that you're mapping over. And once you're mapping over an axis, the only way you can perform an operation along it is by using one of these collectives. So in this case, psum is just a parallel sum. We're saying do a parallel sum over the mapped axis name I. And we're going to divide our input by the sum over the axis name I. And so if we run this, this is just going to normalize our vector. And so we're printing the result, and indeed the sum of the vector entries at the end is 1 because we've normalized it. And collectives work the same on GPU and TPU. Did I? Yeah, good. Great. So I didn't actually include it in detail in this demo, but I just wanted to have a sort of forward pointer for all of you watching. There's sort of a next gen version of PMAP and VMAP. It puts PMAP and VMAP together and generalizes them both. We call it XMAP. And this is something that's like practically, quite useful, even though we have it in this sort of experimental thing for now. I won't go into it in detail, but basically, if you take this idea of like, hey, if I PMAP or VMAP, I can name that axis that's mapped over and then do collective operations over it. One way to think about XMAP is it's just PMAP and VMAP put together. Another way to think about it is it sort of takes this idea of named axis programming to the extreme and lets you sort of bind multiple names. So in this case, this is our simple neural network example, but written sort of with named axes using XMAP. Named axes are cool because they, in some ways make the code more readable. You don't have to remember the meaning of different axis positions anymore. They make a whole bunch of shape errors sort of categorically impossible. And most importantly, the reason why this is sort of in the parallel section is once you have axis names, you can tell XMAP how you want to evaluate it by referring to those names. So if you want to say, hey, I want to vectorize over some of these named axes, but I want to parallelize over other ones. XMAP lets you do that. So it lets you very flexibly write your function once and then change your parallelization strategy. So if you write something with data parallelisms, you're just parallelizing over accelerators using XMAP just in your data batch dimension. And you go into your advisor meeting, and your advisor is like, how would this run if we did model parallelism instead? And we sharded over the arrays themselves and the matrix multiplies. With XMAP, you can just tweak sort of high-level specification and not have to rewrite any of your code to do that. That is the promise of XMAP. Not fully articulated in this demo, but I just wanted to highlight that as like a thing to look for. One other new parallelism API to look out for is pjit. So pjit, as you might guess, is like JIT, but it has a P in the front, and that P stands for parallel. And the idea is that XLA is this compiler. Shouldn't we be able to just say like, hey, I have this computation and I have 8 GPUs. Just compiler, take the wheel. Just make a run on 8 GPUs, whatever it is. And XLA can do that. And here's a simple example of doing that. So here we're going to import this pjit function. This is going to be just a single sort of operation that we're going to parallelize, not even a whole neural network. But this is going to be a convolution. So this is a convolution where it's going to be like 1,000 by 1,000 image, if you like, 1,000 by 1,000 spatial dimensions. Batch size 1, 128 input channels. And then our kernel has 128 input channels, 128 output channels, and a 5 by 5 sort of like spatial thing. So the idea is this is just a trivial convolution on fake data. We can run it and get some results. We can also time it. This is running on 1 GPU because we haven't used pjit yet. Whatever, it takes 53 milliseconds to do this convolution. With pjit, you can express data parallelism, but you can also express model parallelism, or in this case, sort of spatial data parallelism. We want to say, hey, I have these really big high-resolution images. Let's use pjit and parallelize over GPUs, giving each GPU sort of a region of space in my image to deal with. And so the way we're going to express that, we have 8 GPUs. We're going to say, okay, let's think of that as a mesh, like 4x2 devices. And I want to say, take my input spatial features, refer to those things as sort of X and Y, my spatial axes. And I want to map those to my physical resources by breaking up the spatial pieces. Didn't explain that very well, and that's in part because I'm rushing. The high-level idea is that pjit lets you do spatially parallel convolutions automatically. We're just writing conv, and we're telling pjit to spatially parallelize. We have this nice warning in case it has bugs, though to be honest, a lot of people are using it. It probably doesn't have bugs. We get the same results if you memorize a number. We get the same results as in the serial case, 573 something, 573 something. That's great. Let's time its execution. So I wrote this line to sort of place it on, place the image sharded on all the 8 GPUs. And now instead of 53 milliseconds that it takes for one V100 GPU, we can do the same convolution in 10 milliseconds or whatever. And of course, the same thing. Let's see, I'm just going to start executing cells. Runs on TPU. In fact, PJIT is sort of like most battle tested on TPU, and it's actually quite new that it runs on GPU. Yeah, we can take the same thing, big high resolution convolution. We can, test. By the way, these numbers are different because we use NumPy random here. That's not Jax NumPy. Running on a single TPU core, we do this spatial, it's big convolution in 29 milliseconds. And if we parallelize it over all 8 cores using PJIT, it's sort of 7 milliseconds. So again, PJIT, all you have to do is describe how you want your computation to be sharded over physical devices. You can revise this really easily if we wanted to say, hey, instead of sharding my spatial axes in a 2-dimensional way, put all 8, in fact, let's try it. Let's say put all 8, so we have 8 GPUs, take one axis of the image and divide it up into 8 chunks. Before we were dividing one axis into 4 chunks and the other axis into 2 chunks. But let's just try running one axis into 8 chunks. And compiling the first time. Same numerical results. It's about the same amount of time. I guess let's try it one more time. Let's do like only 4 TPU cores, like a 2x2 mesh. Apologies if I get this wrong. Let's say we only had 4 GPUs, or in this case, 4 TPU cores. Let's parallelize this convolution, but we have fewer accelerators. How much time does it take to do? As I can tell, the demo is live. Otherwise, we wouldn't have these boring pauses. OK. And now, it's slower because we have fewer devices, but not that much slower because maybe this example is too small. We have overheads. Cool. So yeah, PJIT is yet another way to parallel multiple accelerators. It's like compiler take the wheel, just like run my big model on 8 GPUs or 8 TPU cores. Cool. That's it for the demo. I have a few more slides. And let's see if I can manage to share my screen. Boom. All right. That was a whirlwind demo tour. Hopefully, some high-level points that got across is like Jax has great tools for your machine learning research, and this idea of like composing up function transformations as sort of like an API that I think is the secret to Jax's power. Plus, new parallelism APIs for scaling are super fun. So people have been doing a lot of fun things with Jax across a lot of domains. I just grabbed some random highlights, possibly biased towards what had nice animations that I could put into slides. But there's a line of work on vision transformers at Google and elsewhere. Those are all implemented in Jax. In things that are a bit further afield, so like in graphics, there's an amazing line of work on these neural radiance fields, or NeRFs. And these videos, I'm sure, are choppy as heck. But for me, they look buttery smooth. And so maybe check out these websites to see them in their full glory. But people are using Jax to sort of train these neural radiance fields. People also use Jax for things like simulation. So there's this amazing package called Jax Md for molecular dynamics. And it's written by people with PhDs in like condensed matter physics or whatever. And it's a cool simulation package. They use things like VMAP to great effect to sort of write simulations on single examples and then VMAP over them to batch them up. When they're having fun, they do things like make simulations of shooting a bullet at the Jax logo in like super slow motion. But more seriously, they also do things like, I think Jax Md was used for optimizing the properties of like photovoltaic materials. Because if you can write a simulation to simulate some like physical properties and maybe measure some desirable objectives from that material, then you can use Autodiff and differentiate through the simulation to maybe optimize properties of your material. Also, AlphaFold, which is kind of a big deal, but the AlphaFold code release was all in Jax. So check that out. In fact, at DeepMind, there's a ton of awesome stuff in Jax. There was a talk at the last NeurIPS talking about the Jax ecosystem, the libraries that they have, but also some of the work that they do. So check that out if you're into DeepMind. I mentioned moonlighting as a machine learning researcher. My contributions were relatively small, but I collaborated on this project on learning differential equations that are easy to solve. And this was super fun with some folks at the University of Toronto. It was fun and a good fit for Jax because we ended up composing a lot of Jax transformations. We sort of added a new one for super high order Autodiff called JET. And then we used JET with ODE and grad and VMAP and JIT. And not shown here for image copyright reasons, but like this tweet has a hilarious GIF meme associated with it. So look up this tweet to see a funny meme about composing function transformations. There's also a Jax Hugging Face sort of hackathon within the last few months, and folks had a lot of fun with it. And they sort of compared Jax implementations of a lot of Hugging Face models on sort of the first three columns here are Jax things, and people were able to write these things and they performed well. But I think actually maybe the most interesting fact is that between these sort of like being able to switch between these columns, especially using 8 GPUs versus 8 TPUs, no changes to the code. And so, you can just try very easily and figure out which things are right for you, or change your mind, in the middle of your project, whether you want to be using GPUs or TPUs. Finally, we entered Jax in the, we made some Jax submissions into this MLPerf benchmarking competition. This is from 2020, so last year. And we made 4 submissions, and Jax was sort of faster. The Jax implementations were faster than all the non-Google competition. This competition is like train actually relatively small models, at least in the year that we did it, but you're allowed to throw as much compute power as you want at at the problem. So these are like training in seconds. So the vertical axis here is seconds. Things like ResNet 50 in 28 seconds. And the ResNet and Transformer in particular, Jax did really well on. The Transformer was like a clear world record. In fact, they retired the benchmark after this like Transformer WMT English-German training benchmark. They retired it after this year. I don't know if it was because of Jax, but maybe. And one of our Jax teammates, my teammate James Bradbury, who worked on this, he actually was training NLP models on the same data set 5 years ago on what he thought was a beefy machine with, I don't know, like 8 GPUs. And to train much simpler models, it would take him like 10 days, for his day job. And then when he worked on this MLPerf submission, he was training actually more sophisticated neural network models on the same data set, but in 16 seconds instead of like 10 days. And so he personally experienced a 50,000 times speed up, of course, using a lot more compute hardware. But like this is sort of showing how far the field has come over just a few years. So with that, I was stopping mode here. I have a ton of backup slides, but I think we're more or less out of time. So thanks for your attention. I'm happy to answer questions for a few minutes.
Cool. Thanks a lot for your talk. So now people on Zoom, if you want, you can unmute yourself if no one else is talking, or write something on the chat. And people in person, you can also raise your hand and I'll repeat the question on Zoom. I'll start with the question myself. So at the beginning, you were mentioning towards the very beginning, you mentioned the JET transform and many like exponentially faster higher order gradients. One, I don't understand how you compute gradients in Jax in such a general way that you can pretty much do a gradient of everything. If you could give more insight into how you do that. And 2, I was curious about the exponential speed up part.
Yeah, right. And actually, I see there's also a question in chat that I think is asking the same sort of thing. Yeah, so it's actually something we've been working on. I've been working on Autodiff for a few years before we started looking at this. So surprising to me, I guess let's try to make a more precise statement. With Jax, you can do higher order Autodiff by composing up something like grad multiple times. You can call it grad, that sort of thing. So you already have a way of composing up and getting higher order Autodiff. It turns out that there's something you can do specifically for example, computing Taylor series terms that is exponentially faster than just composing up first order autodiff. And it's a little surprising, but the intuition is that with sort of when you compose up first order autodiff, you might be asking about different perturbation directions for each. So one way to think about Autodiff is it's sort of doing what numerical differentiation does, but exactly. So forward mode Autodiff, you can ask, hey, if I perturb my input in this particular vector direction, how does my output get perturbed? In what direction? So think of it as like a directional derivative. So you get to specify a perturbation. When you compose up first order Autodiff, you could be asking questions about different perturbations for every order of Autodiff. Another way to think about it is if you want to think about like the Hessian as like a matrix, and like the third order derivative is like a 3-axis matrix. You could contract that third order tensor, if you like. You could contract that against 3 different vectors in general, and ask for what that number is. And composing up first order Autodiff lets you ask that question. But when you ask for a Taylor series expansion, then you're actually contracting against the same vector multiple times, right? You're actually saying like, I just want to know the third order. So when you write a Taylor series expansion, the second order term is like V transpose HV. And like using the same perturbation vector V on all sides. And so that's sort of where the savings comes from. That's one way of thinking about it. There's actually other tricks that are mixed in to actually get a fully exponential speedup. But the idea is just there's a more specialized problem when you're asking about sort of Taylor series. And you can exploit that structure to get computational speedups. Again, there's this detail that I didn't actually mention where what I just said gives you a sub-exponential speedup. But there are other tricks to do with when the primitives you're applying satisfy certain like ODE formulas. Anyway, so Jax has this transformation for, if you like, evaluating Taylor series terms. You can say like, give me the first 5 or 10 or 100 Taylor series terms for this function, and Jax has this transformation to do that. It's kind of like, have you ever heard of someone differentiating to the 100th order? Like, it's not very common. I think there probably are applications out there, but one thing we like to do is, Autodiff research. We used it in that learning ODEs that are fast to solve application because we sort of wanted to regularize the higher order derivatives so that, a 4th order integrator might work better because it wasn't sort of being surprised by how wiggly the higher order derivatives were. So we wanted to like add a regularization term that regularized higher order derivatives. That's why we needed sort of 3rd or 4th or 5th order. Anyway, I'm not sure if that answers the question sufficiently, but there's more details. If you're interested.
It answered my question. I'm not sure. Andrew, did it answer your question as well? They were very similar, I think.
Yeah, it's the same thing. Yeah, that answered my question. Thank you.
It's kind of fun and technical, and I'm not saying this is like the next big thing, but like, if you're into Autodiff, you just want to like learn something fun. Certainly, like, there's much more to be said. And if you send me an email if you want to learn more, or if you have an application for like 50th order Autodiff, we'd love to hear about it. There's some other Jax questions. I know we're low on time, so maybe I'll just try to touch on them briefly. Jax being used in production, or is it still early stages of research? No comment. I mean, like, we're researchers. We made Jax for our own research. Production systems have a whole other set of concerns, and so like, and I'm just not deeply familiar with them, and our team is sort of optimized for building a tool for researchers. So we say that it is a tool for research. You could use Jax in a lot of different interesting ways in sort of like production contexts, and maybe I've heard of people who have done that, but officially Jax is a tool for researchers. I think that's what it's best at, and like that's sort of the value that we can bring is mainly to researchers. That said, I guess one thing that people might wonder in that context is like, how robust is it? Like, if Jax is a research project, we certainly say that Jax is a research project because we like to iterate on it quickly, and we don't want to say it's like a ironclad piece of software. We might change things. At the same time, I think historically it has a great record of being robust and stable, and we love fixing issues very quickly. So I think it has those properties if you're if you want to make sure that the system you're using, even for research, is like reasonably stable and bug-free and this sort of thing. We have a pretty good track record. What is the recommended starting point for people looking at TF PyTorch replacement? There seems to be several competing neural net libraries out there. Yeah, this is a common question. I guess first thing is TensorFlow, PyTorch, those are awesome tools. Nothing but love and respect for the people who work on them. And so like you don't necessarily need a replacement if those things are working well for you. I think Jax, brings some new ideas, and a lot of them are being adopted in TensorFlow and PyTorch. So we think that's great. Also, there's a lot of ways to mix and match these things. In fact, a former colleague just reached out in the last couple of weeks saying, hey, I'm using PyTorch now, but Jax is like way faster for this sort of layer that he had. And hey, can you help me like hook the two up so I can differentiate through it? So it's like an overall PyTorch model, but sort of Jax fast component in the middle. And it was actually really easy. I think if you look at like my public gists on GitHub, you can actually see this example. And I mentioned that just because I don't want to think, sort of a zero sum, like you have to choose one or the other. I'm really excited about ways that these things can be like used together, so you don't have to choose. I guess the other elements of this question is like there's competing neural net libraries out there, Flax, Trax, Haiku, and all this sort of thing. That is like, one downside to Jax is we don't just say like, here's the neural net library to use. That said, I would say if you look at our GitHub README, we say like, here are some of the libraries, the most popular libraries. Try Flax. Flax is really great. A lot of people at Google use Flax. At DeepMind, Haiku is like the standard, and so if you look at a lot of their code, you'll see Haiku used there. Honestly, they're both kind of like pretty similar, if you look at them and have a preference for one or the other, you could choose it. It's actually not that hard to switch between them either. I think if you learn Flax, you've probably learned 90% of Haiku and vice versa. So I would say, dive into those, see the README for like, the Jax README for just links to those things. Yeah, just check it out and don't be too worried about, going down one path and then having to switch later.
It's a bit past 5 p.m., so let's leave it here. Thanks a lot, Matt, for the great presentation.
Yeah, thanks for inviting me.
Good. For those on in person, we'll have a social now with food. Good. Thanks a lot. Bye-bye.
Thanks.